Hey, and welcome to the last part of Chapter 4. So today we're going to talk about 3 topics. I kind of think of this as advanced Lewis structures. It's an idea, well, there's a few different ideas that you want to be able to recognize and in some cases change. Molecules that you've drawn with the Lewis dot structure, like the way we've been doing Lewis structures. So the first situation that we're going to be looking at is resonance. Then we're going to look at formal charge. So we've got our resonance structures and we've got our formal charge. And then we're going to look at polarity. So for resonance structures have delocalized electrons. And they are represented by several contributing structures. So what that means is that you can draw more than one structure, and there's no one reason to say that, like, the left structure is better than the right structure. So here's an example of what we're talking about. Notice in both these cases, we have the same central atom. And in both of these cases, we have some kind of a bond that's going out to an external atom, and they're the same external atoms. So the idea is just that you can just as easily make a double bond written on this side as you can have it written on this side. So whenever you have those situations, and it's more common with oxygen on the outside or other things in that column. But it can happen with plenty of different atoms. So resonance structure is another hint with them that if you want to know if you should expect some resonance structures, they are also very common when you're talking about those polyatomic ions. So things like ClO4 minus, SO4 minus 2 minus. Those kinds of species that have all those oxygens, it's very common to have resonance for those ones. All right, so when we look at resonance structures, we will draw 2 of them, like as shown here, but you're going to do a back and forth arrow written between them. And what you want to recognize is that even though we've drawn 2 structures, the electrons aren't fluctuating. It kind of looks the way we've drawn like they're fluctuating. This is just the standard form that we use to write resonance structures. It looks like they're fluctuating, but they're not. So the electronic structure right here, this is always the average of all those shown by the resonance form. So in this case, there were 2, but you could have 3, 4, 5, depending on how many bonding positions you could move that double bond to, or you could show it. You're not really moving it, you could show it between. What does this mean and why do we care? Well, what we found in studies is that, remember there are those tables and tables and tables of information in chemistry? Well, right here, here's some information from a table. We find that NO has a bond length of this, that's a picometer, so it's like really teeny tiny. He has that bond length. So what we're saying is that this bond length right here is 140. And then the double bond has a bond length of 121. And what we found is that when you measure these in real life, they are neither 140 nor 121. It's the average. So all the bonds in the NO2 molecule, all of them, have the bond length of about 130. And if you Google it, you can get numbers that vary, but they're about 130. And another way you can think of it is that you can say each bond in the resonance structure is 1.5 bond lengths. So if you count this as one bond, and this is a bond, and this is a bond, so see that's a total of 3 bonds. So, and they are between 2 positions. So each of the bonds is 1.5 bond lengths. That's kind of how you can think of it. So just a quick little note here too, that a longer bond, and that is the single bond. Notice single bond. A longer bond is weaker. And a double bond, so that one's the shorter bond. Shorter bonds are stronger. It kind of makes sense because you can think of like the electrons are being held more tightly between the atoms in the double bond. There's extra electrons in there. And if they are shorter, then there's less space between them and the surrounding atoms. And so that means they're closer to the opposite atom's nuclei, so they're held more strongly. The other thing to say about the resonance structures, along the idea of it's not fluctuating, but it's the average, is just to say that you could say that when you look at a rhinoceros, it may look like a cross between an elephant and a unicorn, but we could all say that a rhinoceros, which is the in-between picture of these two pictures. So whatever the average is of those ones, the rhinoceros has its own unique characteristics and properties that are different from a unicorn and also different from an elephant. So you want to go back and look at your sheet and find any situation like this where you have the same atoms on the outside, singles, doubles, and make sure you mark the column that they're resonance. Make sure you put the back and forth arrow. These brackets, by the way, are only for things that have charges. So if your resonance structures have charges, you need a set of brackets on every single resonance structure as well as a charge written on the outside. Okay, so now we're moving on to formal charge. So formal charge is another situation you come up with when you are doing structures. And again, this is a situation where when we looked it up and we look the molecule, some of our predictions aren't quite what you get in real life. And so I know it's kind of a way to deal with that. So the formal charge of an atom in a molecule is the hypothetical charge. So it's not a real thing, it's a hypothetical thing. And so what the atom would have if we could redistribute the electrons in the bonds evenly between the atoms. And again, it's not the actual charge of the atom. It's just the hypothetical charge. And when it comes into play is when you have, again, the oxygen on the outside. And the key thing is that you're going to have an element in rows 3 through 7. Now, you can also have it in other situations, but I'm just saying if you have a polyatomic ion, again, like an SO4, something that can do more than it's 8 electrons around the middle, something that can do hypervalent or expanded octets, you might make sure you check the formal charges on that situation. It also comes into play when it's possible to draw more than one structure. You'll see on the next page an example of that. But before we go on, we're going to review how to do the formula. The formula, it looks like a complicated formula, but it's actually not a complicated formula at all. So for formal charge, you're going to do it for every atom in a compound. And so, for example, for the chlorine, I would say that the valence shell electrons for chlorine, it's in the 7th tall column, so it's 7, minus, and now it's talking about the lone pair electrons. So this is all of the lone pair electrons. So I have 1, 2, 3, 4, 5, 6. 6 lone pair electrons. And then minus half of the bonding electrons. So remember, there's 2 electrons in that bond. Remember, don't really draw it that way, but I'm doing it so you can see it. So half of the 2 electrons is just that we have 1 electron. So our formula would be 7 minus 6 minus 1, which gives us 0. So the chlorine has a formal charge of 0, and that's great. We want it to have a formal charge of 0. You want to get to the point where you can look around the molecule and you can see that these other chlorines are going to have the same formal charges. Notice that they have the same number of electrons as lone pairs as well as the ones in the bonds. So it turns out that all of these chlorines are 7 minus 6 minus half of 2. And the same one here, 7 minus 6 minus half of 2. I meant to put a 0 over here, sorry. And those are all great. Those are great formal charges. Now we're going to look at the boron. And so the boron, he has 3 valence electrons, that third tall column. And then we're looking, does he have any lone pairs at all? He doesn't have any lone pairs. So that would be 0 lone pair electrons. He has none of the electrons are lone pairs. And then we would say that he has 1, 2, 3, 4, 5, 6 electrons in bonding position. So half of 6 is, that, if you don't remember, that's 3. So the whole thing comes out to be 0. 3 minus 3 is 0. So the boron is 0. So the way you write these, if they aren't 0, is you put them in and you put a circle around them. But when they are 0, you just don't even write them in. So the only time that it's important is when it's not 0, basically. So you want 0. Zeros are good. You just don't want to write them in. We're going to look at another molecule that also has 0, and then we're going to show you the little bit easier way of thinking about it. So hydrogen. Hydrogen has a total of 1 valence electron. Notice again, he doesn't have any lone pairs all around him. So he doesn't have any. So that's 0 on his lone pairs. And then his number of bonding electrons, there's 2 of these in the bond. So half of 2, that'll be 1, is 0. It's going to be the same case for this hydrogen over here. He's also going to be 0. Because he's 1 minus 0 minus half of 2 again. And then we have the oxygen, and the oxygen is, he's got 6 total to begin with. He's got 1, 2, 3, 4 lone pairs. The lone pairs count all the way. And then he's got 1, 2, 3, 4 in the bonds. So 6 minus 4 minus 2 is 0. Another way you can think of it that I've seen people do is you can say that it's valence minus dots minus lines. So you don't have to think about everything. So for like the boron example, valence is 3. He has 0 dots, and he has 1, 2, 3 lines. So it'd be 3 minus 0 dots minus 3 lines, which still gives you 0. And if you're going to do it for this one, he's 7. He's got 6 dots, and he's got 1 line. So that's 0. And I had another way that I showed in class that I've also seen people do. It was kind of a method I kind of came up with. And it's where you put your pencil on top of the element you're counting, so like right here, and you state the valence, which would be, for boron's case, I'm going to erase these so they're not confusing. In boron's case, it would be 3, and then every time you count something, you count down. So 3, 2, 1, 0. So boron is also 0. Then if we go over to the chlorines, let's switch over here, and so chlorine is 7, 6, 5, 4, 3, 2, 1, 0. So he's 0. I'm going to do it to the oxygen. So the oxygen, I stick my pencil in the middle and I say 6, 5, 4, 3, 2, 1, 0. So he's 0, like we expect. And then hydrogen, I stick my pencil 1. And he doesn't have anything around him besides that 1 bond, right? So he's only got the 1 bond. So when I touch the bond, so he's 1, and it goes down to 0. And you can keep going below 0, so you would have to count like to -1 and -2 if you have more than what the allotment is. That method will not work unless you state the valence and then start counting down. If you start touching something like that the element is touching first, it'll mess it all up. So overall, that was like an extra shortcut, but definitely I would recommend, like, if you need a shortcut, like, think of it like this, it might work for you. All right, so predicting molecular structure with formal charge. So we have steps for writing the Lewis structures, and sometimes you end up with many possible structures. Here's an example down here of where you can end up with many. All of these lead to having the same number of electrons. So this one is 2, 4, 6, 8, 10, 12, 14, 16. 2, 4, 6, 8, 10, 12, 14, 16. 2, 4, 6, 8, 10, 12, 14, 16. So see, they all have 16. So that means with what we're doing right now, there's lots of possibilities. So how do you know which one? So this is the other reason formal charge is very useful, is it helps us to know which one and to predict the bond lengths correctly. So molecular structure is one in which all the formal charges are 0. That's what you want. You want everything to be 0. But if it has to have non-zeros, so if it must have non-zeros, the arrangement with the lowest non-zeros, and also I would add in and closest to 0. So you want the lowest number of them, but you also want the actual lowest value. So like ones or negative ones are better than like, 2, 3, 4, like those are really bad formal charges. It would be very unusual to have a formal charge that high. Then, the third step is the Lewis structure is preferable when adjacent formal charges are 0 or of the opposite sign. I'll show an example of that one. It's talking about something like this, but there's a reason we would have ruled this structure out, that it's better for these opposite signs to be beside each other than across from each other. But we would have already ruled something out. I'm going to show you how these work in just a minute. So that final structure is not the correct structure. But all things being equal, you would choose that final structure. And then the last one is the formal charge with the negative, the structure with the negative formal charge on the more electronegative atom is preferable. There's a molecule we did that's a radical and it's on the chart. It's like the last one on the chart. That's where this last rule comes into play. So these are in order, and if you get a rule that applies, stop. Don't keep going on. So for example, rule 1, a molecular structure in which all formal charges are 0 is preferable. So if you look at these pictures, we already have something that has all zeros. Stop at that rule. Nothing else has all zeros. That means that this is the correct structure. And you're done. Now, let's say that we didn't have that option on the left. You can cover it up with your hand. If you didn't have that option, then you would go on. So then it says the Lewis structure with the most non-zero formal charges. Well, here we've got 1s versus 2s. So then your second choice, but again, you've already chosen the first one. I'm just trying to give some examples. Your second choice would be this one. And then you've got your third choice, the Lewis structure preferable when adjacent formal charges are 0 or the opposite sign. So you'll notice that these are 0 and they're the opposite sign. But again, that would be your third choice because the first rule applied to the first one. Hoping that all makes sense. And also just as a quick counting practice, so like right here, let's count carbon to make sure that we come up with this formal charge. And let's make sure that we also put the formal charge the way it would look on the molecule, even though this isn't the right molecule, obviously. So for carbon, he has 6 valence electrons minus 4 dots minus 2 lines. I'm sorry, he has 4 valence electrons, doesn't he? I am not thinking today. So carbon has 4 valence electrons minus 4 dots minus 2 lines, which gives me negative 2. Or I can say 4, 3, 2, 1, 0, minus 1, minus 2. So the way we would list this, if this were the only formal charge, is we would put minus 2 and we would put a circle on it. So this is different than charge. This is different than when we talk about polarity. This is formal charge. It's not a real thing, but it affects real things. It's kind of weird. And then like for the oxygen right here, the oxygen is 6 minus 0 dots minus 4 bonds. So he would be plus 2. And again, we would put a circle on him. And then over here, this is for this oxygen, this one is 6 minus 6 dots minus 1 bond. So that's the minus 1. So it would have been listed like this with a minus. And then over here, this is 6 minus 2 dots minus 3 bonds is 5. So this is plus 1 right here. So hopefully all of that all makes sense for the formal charges. All right, so the last section that we're going to be looking at is polarity. But before you get to that, go into your chart and look through your molecules and double check the formal charges. The last page, especially the ones that I have highlighted with the same color on the left side, on the last page, those are ones that you definitely need to look at and check all the atoms for their formal charges because something changes for all of them. All right. Now we have polarity. Polarity is a real thing. Polarity does not go away. It's something you will see in Gen Chem 2 because it affects properties of elements. It's something that you will see in organic chemistry. You'll see it in biochemistry. It's kind of huge in the human body. Polarity is part of the reason why water molecules will dissolve sodium chloride. Kind of a big thing. And it's because on a water molecule, this bond right here, it's not sharing those electrons evenly. So if I zoom in on that water molecule, and if I make the electrons like blue, so up until this point, we kind of talked about the covalence as kind of being shared, and we were implying that they were shared evenly. But oxygen is much more electronegative than hydrogen. And what that means is that the oxygen will take those two electrons, and instead of letting them being shared evenly, whoops, took too much out there. All that it'll do is that it'll pull the electrons towards itself. So the hydrogen can still feel those electrons. It's still part of a shared bond. It's not like they aren't still being shared, but they just are being shared unevenly. And again, because they're not transferred, we can't say that oxygen becomes literally more negative, but he kind of sort of becomes more negative. We call it a partial charge. And so we indicate it with a delta, and I'm not great at deltas at all. It kind of looks like an S, but that's supposed to be a delta. And you would say that the oxygen is negative in that bond and that the hydrogen is positive. And again, over on this one, the hydrogen is the positive one. You don't use twos, though. I know that it looks like you should say 2 is the negative. We just recognize that that's the negative side and the bottom is the positive side. It's because this kind of sort of positives, we're not trying to talk about multiples of kind of sort of positives or kind of sort of negatives. The other way that this can be illustrated is with an arrow. And so if you take an arrow and you put a plus sign on one half of it, the arrow points towards the negative element, and the plus side of it is on the positive element. You don't usually have them both in the same molecule. So you either have the method that uses the arrows or the method that uses the signs. So here's an example here with the arrows. The arrows help us to see the direction of the bond. And so I've got this going up and this going up. Something I haven't drawn on this is that this oxygen already has 2 lone pairs, and that's why our bonds aren't going out symmetrically. So polarity happens anytime that the electrons aren't being shared evenly. This is a polar bond. And the reason that water can dissolve a salt is because it not only has a polar bond on both sides, but they're angled against each other, so they aren't being shared equally. If this had been this molecule, so you'll notice these guys are across from each other. So even though these electrons aren't being shared equally and they're sitting more over on this side of the bond, so both of the electrons are more over here in that bond. Again, don't use dots for the bonds. I'm just trying to illustrate something. It's like a tug of war. So imagine that there's a tugging going on the one direction, and the carbon's holding on, so there's a tugging like that, and there's also a tugging like that. You can see that they cancel each other out because it's an opposite tugging. If you had 2 things pulling equally on opposite directions, they cancel. So even though these bonds are, yes, polar, the molecule overall is non-polar. The biggest issues with polarity comes in because of those lone pairs. We're going to go back up over the water example. Again, we've already said that there's a polar bond, and instead of there just being polar bonds, those polar bonds also influence the whole molecule. And so it's easier, again, to see this left picture. What we're saying is that there's a kind of sort of positive side of the molecule and a kind of sort of negative side. And you're like, what does that matter? Well, it matters because the water molecules will line up. So that their negative sides are against each other, and they'll line up sideways this way and up and down. This structure increases the boiling point of water from what you would originally calculate for it. There's other things that also influence it, called hydrogen bonding, but this is one thing. But the other thing is that when you put sodium chloride or any other kind of a salt in water, that partial positive and partial negative is just enough to tie up these guys. And so we can take the sodium chloride right here, and we can take him, and he can hang out over here with the negative, and because they're attracted to each other, and this guy can come over here, and he can hang out with the positive side over here. And what that means is that our salt is dissolved. And you could kind of think of the strength of the salts being staying together or dissolving in water is related to how strongly attracted they are to these different parts of the water molecule. So it's kind of a cool thing. But that's why it matters, because sometimes it just helps to know why it matters, this and why we talk about it. So this isn't going away. You'll see it again. So you need to understand polarity. So we're going to take a step back, and we're going to look at the bonds really quick. And again, these are some great videos on this topic. We are not doing this Newton homework on it. So electronegativity is the measure of how strongly the atoms attract bonding electrons to themselves. I was showing that in this example down here. Remember that the noble gases they do not have an electronegative value. That's one of the reasons they actually don't do very much bonding. The lower noble gases, you will see that we've got xenon in a few examples, sometimes krypton. They can do stuff. We can finagle things to make them do stuff, but they don't have official electronegative values. Now, to figure out the change in electronegativity, it looks all fancy right here. That's just the difference between two atoms is electronegativity. So if you look at sodium, his value right there, look, it's 0.9. And if you look at chlorine, right here, over here, look, it's 2.5. So it's just the difference. I'm sorry, I grabbed carbon. I'm having all kinds of problems. It's 3.0. So if you look at the difference between those two, it's 2.1. So we've got some other molecules. Make sure that you can look on the chart and see that these values are the ones on this chart. Also remember that you can find other electronegative charts. Your homework might have a different chart because it's that outsourced program. But you can find other electronegative charts. These values might vary just a little bit in the decimal place region. So we've got these values solved for. So make sure you're clear on where these values came from and that you can do this calculation. It's just real simple math. And then we want you to do this. We want to find what is less than 0.4, and we call this a pure covalent bond. So you'll notice right here, the hydrogen-hydrogen bond, anytime you have the same element, they are going to be shared evenly. The electrons will be shared evenly. And hydrogen is actually misplaced. Hydrogen, we've got it floating here, but he actually kind of fits right here. So hydrogen, chlorine, their bond and their difference is this 0.4. And what we can say is like the molecule doesn't recognize that as being a significant enough difference to convert to polarity is kind of a way to say it. Some people will debate that this number should be 0.5. Some people will debate that it should be 0.4. Anyways, we're saying 0.4. And I'm putting a line to say include 0.4 in the pure covalent. As a note, things that are pure covalent, these are things that are nonpolar. Like oils. So nonpolar will dissolve nonpolar. Oils like oils. Oils don't like water. So if we're trying to mark our pure covalents with this color, it's going to be here and here. Now our polar covalent, right here, this is what's falling between that range. We've got it here and here. And then last but not least, we kind of have this last category. We've already talked about ionic bonds. We would expect Na and Cl to be ionic because they're on opposite sides of the chart. So we've already talked about this, but we're giving a numerical value to prove that those electrons are not really being shared and they are being transferred. Just keep in mind that this middle section is very important and it leads to a whole lot of properties. So you need to be able to look at molecules, you need to be able to look at their bonds and figure out whether or not their bonds are going to lead to polar bonds and then an overall polar molecule or an overall nonpolar molecule. So if you go back to your chart and you look at your chart, you're going to check mark things that lead to polar and nonpolar. I've got a rule of thumb on the next page, but just bear in mind that most things There's two exceptions. But most things with lone pairs, they're going to be like skewed off. Like the lone pairs are going to be taking up space, and it's going to make your bonds kind of go off of like a straight axis. And so most things with lone pairs are polar. The exceptions are going to be a square planar. You can get to square planar with lone pairs. And then also there's a certain linear one that you can get to with lone pairs. And of course, if you think about those two shapes, if you have something in the middle and then the square planar, like if we're looking at the top down, that's the one that looks like this. So it's like perfectly, everything is perfectly opposite each other. Whoops. So it's like these two guys can cancel each other out. And then the other set can cancel each other out. So it's like perfectly, I'm trying to kind of make them look flat there. So that's the square planar picture. Even though I have up and below, I have a lone pair. And then the other picture is, again, something linear. And that's where you've got a axis. And you do have there's a situation where you can have lone pairs all around that atom, but still be linear. And again, that linear look, that look of the thing, that's going to be something that is also nonpolar. So this is nonpolar, and this is nonpolar. And those are kind of your only nonpolar possibilities when you have lone pairs. So lone pairs are usually polar, except for those two cases. And then, and that one's called linear. And then the other situation that you can go to get something that's nonpolar is basically no lone pairs and all the same atoms. Notice in the example we have right here. So notice with this carbon example, there were no lone pairs on him, and that meant the bonds could be perfectly situated up from him. Another example, just to show you like a bigger example, if you can imagine something in the middle of something, and imagine it's being pulled apart by 6 strings, if you like, or 6 tug-of-war ropes, but they're all perfectly displaced all around. So if that happens, and they're perfectly like even all the way around, the A isn't affected. And so, like this guy, it's canceled with this guy. This guy is canceled with this guy, this guy is canceled with this guy, and this one's canceled. This one is canceled with this guy. But everyone has a cancel, and that means that we are also nonpolar. All the other cases are polar. If you had to guess, and if the atoms weren't the same, and if you had lone pairs, especially either of those cases, I would guess polar if I had to guess. So this is just a quick review on that idea. So here's 2 ways that we can talk about the bond dipole. We can either use the arrow, which means that this is the partial side that's positive and that's the one that's negative. That's the negative side, that's the positive side. But don't use circles with it. Sorry, I shouldn't have used a circle. Or you can use just the little deltas. So most bonds, if they are different elements, most bonds will have a dipole. But remember, if their difference is this 0.4, under 0.4, then it's not considered having a dipole, which means it is not, you don't have any polar bonds. So a bond dipole means that you have a polar bond, but it does not mean that your molecule is polar. Different things. And again, this is just repeating what we said. As the electrons are pulled towards the more electronegative atom, one atom is left with a partial positive charge, the other one is partial negative. And we call it a dipole because 2 poles, like a magnet having a positive and negative pole, dipole, dipole. And so we've got these 2 over here. Notice that here's our 2 poles. That's our positive, and partial negative. And then again, this is reviewing that idea of an overall molecular dipole moment. Notice that this molecule, same atoms, no lone pairs. Notice that that tug of war, it's an even tug of war. And overall, even though the bonds are polar, again, the bonds are polar. Overall, there's no dipole moment. And then over here, if you look in the moments, overall, we have an overall, this is our overall dipole moment. So we have we have the one here, we have this one here. They kind of add together. Notice we have the same atoms, but we had some lone pairs that skewed off those atoms, which the bonds, like where they placed, which gives us that overall dipole moment. Remember that overall dipole moments have a lot of big causes. All right, so this is like my overall statement, and I had to change this in class because I just did not word it very well. I just told everyone, like, assume something's polar unless square planar or linear, and again, same atoms, or if you have known lone pairs and you have the same external atoms. And then just a review on why do we care? They tend to align when placed in an electric field with the positive end. So the positive side of the molecule will be oriented towards the negative plate and the negative part of the molecule towards the positive plate. This is a separation technique that we use that's super helpful. You can also use an electrically charged object to attract polar things, but not nonpolar. So if you have like a mixture of something polar and something nonpolar, you can separate them. We talk a lot about separation in chemistry because when you do reactions, you end up with mixtures. And usually it's one thing you want and one thing you don't want. So the separation techniques are important. It also provides structure for certain liquids to line up, positive and negative. We already talked about that. And that affects the properties like boiling point, viscosity, all those kinds of things. And then polar liquids are better at dissolving polar substances. And then nonpolar liquids are better at dissolving nonpolar substances, like dissolves like. So water is a polar liquid, and you can think of NaCl as a polar, kind of an extreme polar. It's ionic, but it's an extreme polar substance. Also, ionic compounds can dissolve in polar compounds, just like what I was saying, such as water. And that'll be in the next chapter. We've got a few Newton comments, and that is the end for this section. And I'm going to go and pull up the chart and kind of talk about the chart too.